facilitating today's webinar. If you have any questions throughout today's presentation, please type them into the question box on the GoToWebinar panel located on the right side of your computer screen. We will try to get to as many questions as possible before the end of today's webinar. This webinar was brought to you by the Rely On product family. ABB Protective Relay School Webinar Series Disclaimer. ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay schools, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and sales representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Please contact an ABB sales representative for further information. Today's webinar is Bus Protection Fundamentals, presented by Jack Chang. Jack is the Regional Technical Manager for ABB in the Substation Automation products, serving customers in Western Canada and the Northern regions. He provides engineering, commissioning, and troubleshooting support to customers applying ABB's high-voltage protective and automation devices. Prior to joining ABB, Jack worked as a substation P&C project engineer in 2 specialized consulting firms, and also as an engineering consultant to a public-owned utility and their transmission, expansion, and upgrade projects. Jack is a registered professional engineer in the province of Alberta, Canada. And now we will give the presentation over to Jack.
Thank you, Carrie. Hello, good afternoon, everybody. Thank you for attending today's webinar on Busbar Fundamentals to Busbar Protection. Here are the learning objectives for the next 1.5 hours. Relatively speaking, this topic is lighter than the one I presented a couple weeks ago on generator protection. So, I don't expect any problem to finish on time and with plenty of time for questioning. So feel free to submit your questions, if any, and I have my emails here. If you have some question you would like to discuss on your specific application, feel free to send me an email or give me a call. Okay, the objects for today: type of bus configurations, current transformer characteristics and their effect on bus protection, types of bus protection schemes, and modern numerical bus protection features. Basically, modern numerical relays in bus protection relays. So why do we need bus protection? Decades ago, bus protection probably was not a strict requirement for utilities. Faults on the bus usually can tolerate certain amount of delays from backup protection, from the main equipment protection, such as transformers, such as lines. They can provide a decent, relatively fast, but with time delay, bus protection. Okay. But nowadays, with the power systems, equipment being operated really near their rated limitations and the increased short circuit level and its impact, and therefore the impact on system stability, really the significance required, the busbar protection really has become a requirement for modern, substation, especially high voltage substation, extra high voltage substation protection design. On medium voltage or low voltage switchgear busbar protection, now it also has become a necessity because of the security requirements, because of arc flash related security requirements. If the switchgear is not equipped with arc flash protection, for example, dedicated light sensor, laser sensor sensing arc flash protection, busbar protection typically are required in order to reduce the damaging sound and the light and the heat waves projected from the any arc flash scenario condition. So in general, but however, the good thing for busbar protection is any fault on the busbar typically are very robust with high current forces, so relatively easy to detect. With sensitivity, typically is not an issue. As I mentioned, on the high voltage, extra high voltage stations, the busbar fault need to be cleared very quickly, usually within a cycle, because it has network stability concern. It will cause pulse slip on nearby generator, especially on those busbar at the near the generation plane. For example, at the switching yard of any large generation plant. Bigger fault related to damage and risk to human life or injury. That's needless to say. And many busbar can be caused during maintenance. You accidentally drop the tool or something on the when you were really doing maintenance work on a metal clad medium voltage switchgear. You accidentally drop the tool or wrench or something. It can cause damaging arc flash effect. So the busbar protection in that case can save your life. Again, busbar protection is easy to detect because of the robust and high short circuit level, high current nature. Easy to protect for internal fault. Usually for busbar protection, we all know that you use the differential concept to detect the fault and thereby to clear that in a very speedy manner. However, because of the typically the other characteristic of busbar is that really a piece of busbar is really no significant impedance involved. Unlike transformer, reactor, or lines, because of the distance involved, because of the amount of the magnetic cord involved, there's significant impedance involved. So depends on where the fault is. Really, the fault current could be different. Okay? So usually, for example, on the transformer, if you look at from the high voltage side, really for the fault right in front of the primary high voltage bushing compared to the fault at the low voltage bushing, really the fault current can be detected sensed by the high voltage CT really very significant because of that impedance. However, that's why on the contrary for the busbar, really there's no significant impedance involved. So really the fault current is the same. It doesn't matter regardless which CT actually is sensing the current. So in other words, for external fault on the busbar protection zone, the outgoing CT is very likely to saturate because it is sensing a significant amount of currents going through it. However, so that's why busbar protection must be very selective. It cannot operate under unwanted external fault situations. Okay. Next. And extra challenges posed by busbar protection are the numerous myriad of bus configurations that existed out there. In here, I summarized a few that's most commonly seen, and the asterisk or the star sign indicates the busbar configuration that you would probably see most commonly in North America, in Canada, or in US, which you have your single bus, your double bus single breaker, which we see more and more in the switchgear, the GIS switchgear right now, and breaker and half, and ring bus. Okay, and breaker and half and ring bus are typically being designed for high voltage and extra high voltage substations. Okay, so single bus, you have the breakers. Each breaker, you have the feeders protecting one. You only have one bus source, so it's very simple. Main and transfer bus, we don't see this a lot. You probably would see this very often in Europe, but we don't really see this stuff, so that we see this type of configuration a lot, so we can skip it. Double bus single breaker, as I mentioned, typically you have become to see this type of configuration more and more in the GIS switchgear. Actually, the characteristic is that you can have two independent bus zones depending on how you operate your feeders, how you connect your feeder. Each feeder can be connected to bus bar 1 or bus bar 2. So that adds extra complexity to the bus bar protection, because the bus bar protection must know how many CT, how many feeders are currently connected to that particular bus bar. So with modern bus bar protection, numerical bus bar protection relay, you always have this so-called dynamic zone switching feature that depends on the disconnect switch's position. The bus bar will know that, okay, this feeder number 1 is currently connected to bus A. Feeder number 2 is connected to bus B, and so on. It's very important to know that. Also, you also need to know that when the tiebreaker, for example, that's closed here, if tiebreaker is closed, it has to know that now the two bus zones are being merged into one. So whenever there's any fault happen on any of the bus bar, all the feeder, all the breaker need to be up, need to be open, need to be true. So typically these type of logic is important, and commonly it's very cumbersome if you want to develop your own logic using certain programmable logic functions in the modern relay. But typically for modern busbar protection, there are a dynamic zone switching feature that take care of this. Double bus, double breaker. We don't see this a lot, but breaker and one half type of configuration. We see this plenty, typically in extra high voltage substations. So basically, for this type of bus configuration, you need dedicated bus protection for each of the two main bus bar on the top and on the bottom. And for the other bus bar, we call that stub bus. These stub sections, typically they are already properly protected by the equipment protection by overlapping the two CPs. So this can be a transformer, it can be a line, it can be a reactor, it can be a capacitor, but anyway, they have all been properly protected. You don't really need a dedicated bus bar protection, but you need a dedicated bus bar protection for the main two bus bars. And this is the ring bus, and typically ring bus, again, just similar to the breaker and half, for the ring bus, you do not really need a dedicated bus bar protection. All these bus stub sections can be protected properly by even redundant protection from the equipment. Okay. So similar to breaker and half. And this main time main is a very popular or common bus configuration in medium voltage or distribution level substations. So basically, you have two sources. You can have more than one, more than two, but typically you see two sources from two transformers feeding the two bus bar. And then you will have the tiebreakers. The tiebreaker can be operated normally open or normally closed. Okay, and typically you will have CT on each side of the tiebreaker to form two independent, distinct bus zones. Okay, so that's the ideal scenario. But you can also see in some situations you don't have the overlapping CTs across the breaker. Now that could pose some problem. But every problem we do have modern solutions to come to that. So we will introduce that later. Okay. So there are some issues with busbar. Okay, availability of overlapping protection zone CTs. That's what I just mentioned. The blind or end zone protection. These two we'll introduce a little bit later in today's agenda. The loads for sources we switch from one bus to the other. Remember I mentioned that on the double breaker, single breaker double bus scheme. Any CT can be switched freely to either of the sources. So the bus protection will know and take care of that. The bullet 3 and 4 are basically talking about the same thing. Current transformer switching from one zone to another. Okay. The open circuit current transformer, what you want do you want to block? Because once the current transformer are open circuited or short circuited, basically you lose that source, that feed to your relay coil. So you have to take care of that. Either you block or you do something about it. Alarm or block. And CT saturation, how modern busbar protection accounts for CT saturation effect. Zonal protection is the fundamental zonal protection theory for protections. As you can see, there are multiple zones, and the bus zones are shown in green. The green are the bus. So typically, you can either deploy dedicated busbar protection, or in some, or as I introduced in some in green. For example, breaker and half or ring bus configuration, you don't really need a dedicated. Those zones can be protected effectively by your equipment protection. Again, zonal protection. Now, if you take a deeper look at for a main time mains type of substation, and imagine that this is the tiebreaker. Okay, this is the tiebreaker. If you have an overlapping set of CT like this, okay, the fault happens right beside one CT and the breaker. Obviously, will pose no problem at all. Both zones, both relay, both busbar protection relay will operate and open the breaker and take out the fault. So it's good when you have overlapping CT like this. It's no problem. However, if you think about it, because remember, if I mentioned before that for this type of scheme, the bus configuration, typically sometimes the substation will operate with this tiebreaker normally open. Okay, it's not closed, it's open. So when you operate a main time main scheme with the breaker open like this, normally open, a fault right as indicated here between the blue CT and the breaker and the open breaker, then in this case the blue zone will operate. Correct? But the blue zone will operate. But really, if you think about it, if the breaker is open, there's really no reason. It's unnecessary for the blue zone to operate. The blue zone could have been continually put in service, without being disturbed by this fault. The green, because as soon as the green zone operates with the open breaker, the fault is clear. Okay, so we call that, this is called the blind zone, and then this effect, this tripping effect for the blue zone protective relay is called over tripping. So ideally, we would like to avoid that. Okay, and we have a solution, and we will introduce that later. In some unideal situations, you only have, I don't know, I typically for you do not have the overlapping CT on this side of breaker. Typically, this probably does not happen, would not happen very often for switchgear type of bus bars. Usually you see this a lot for example, for a breaker and half type of light tank type of CT. Light tank type of CT, because of a cost, you would typically not install light tank CT on both sides of the breaker. Okay, because CTs are expensive, especially for light tank type of CT. You need an insulator, you need a steel, you need a stand. So typically you will only have CT on one side. So you see this a lot for light tank type of CTs. Okay. So for the fault like this between the CT and the breakers, okay, that's a very short section of bus bar. Okay, it is a bus bar, so you have to take it out fast. The blue zone obviously will operate for this fault. Okay, blue zone will operate for this fault and trip all breakers in the zone, including the tie. That's, for example, that's discuss the situation when this breaker is closed. But as you can see, the green zone will restrain, okay, because it's considered external to the green zone. So once the breaker is open, the fault's still there because the green zone did not operate, did not take out the fault. The fault's still there, even though the blue zone operates already. Okay. So we have to figure out a way how to force the green zone to open. Okay. In this case, if you can tolerate certain delays, then the blue CTs, you can rely on the breaker field protection to take out, to take out this to take out the green zone, to open the green zone breakers sequentially with time delay. But however, if you need some type of prompt instantaneous busbar protection for this fault, then you need some certain type of logic, or we call it end zone, blind zone protection, which again we will introduce later. Again, that's when the breaker is closed. If the breaker is normally is under open conditions, what are you going to do? The blue zone will still operate again unnecessarily by overtripping. It doesn't really need to open, but it has to because the fault is in the blue zone. However, when the breaker is open, and the green zone again will still restrain. So even for the breaker is open in this condition, blue zone overtrip without really clearing out the fault. So it really doesn't help alleviate the fault stability problem. Okay. So concerns for bus protection about current transformer, as I described earlier, explained a little earlier, the CT for bus on the bus bar is really prone to saturate during external fault. So here is some common knowledge on CTs. I'm not going to drill too much into this because this is just to introduce, to get all of us on the same page on the CT characteristics. So basically, we have our accuracy class with C. C class CT basically means that you can interpret your CT knee point, saturation voltage, right from the curve. Okay, the voltage, the excitation voltage, and the excitation current curve. Okay, you can interpret directly or extrapolate directly right from using the curve. Basically, the standard for the CT are C57, okay, 13, and one is application, one is guide for application, one is basically standard. So what does it say about the CT? For example, for a 1200 to 5 CT with rated 800 volt C-class CT, this current transformer is rated to deliver 800 volt, which is your rated voltage on its secondary when it's connected to standard burden. Standard burden means with 20 times of the current, with a 5 amp rated secondary current CT, 20 times is 100 amp, so your rated burden is 800 divided by 100, which is 8 ohms. This is your rated burden. So what it's saying is, this CT guarantees a certain accuracy, which is 10% for C-class, while allowing 20 times rated current to a standard rated burden that is 8 ohms. Okay. And with different, obviously different CT rated voltage, you have different CT rated burden, standard burden. With C800, you have 8 ohms, 400, 4 ohms, and so on. Here, as I mentioned before, for C-class CT, you can interpret the knee point voltage and the saturation voltage right from the curve. Okay, so this is the log and log plot that you will see commonly for any CT. Okay. So, what is the difficulty to measure differential curve? So there are in general 3 dimensional conditions. This is basically applied in general to any differential type of measurement action philosophy. Basically, under normal load flow, there should be no differential current. The relay should be stable. Under external flow, there will be high current flow through the zone. However, because it's in and out, your protection has to be, your differential protection has to be stable as well. However, because of external flow, there is possibility that one of the CT could saturate, and the saturated CT would provide distorted the secondary current that could jeopardize the stability of the relay. Okay? For internal flow, obviously, all the currents are going through the fault inside the protection zone, the relay definitely has to operate. So you will have high differential current. So I'm sure this is the common differential philosophy that actually accounts for all type of differential application for lines, for buses, for transformers. They all the same. So upon CT saturations, you will cause false differential current for external fault. What is CT saturation? CT core can reach saturation flux density due to a combination DC effect or with the possibility of remnant flux. Okay. The remnant flux is the existing flux inside the CT core that you cannot really predict, but you have to assume and estimate and allow room for it. That would either counter or help your CT saturating margin. So typically, as a protection engineer, when you are calculate relay setting, differential setting, you would actually design or calculate from a conservative aspect that you assume that the CT actually go against. The remnant flux actually go against you. That actually reduce the size of your core. Actually, make your CT more much easier to saturate. So basically, you account for that using your differential setting, your slopes. So basically, because the CT saturates, the output current suddenly changes from a proportional signal to zero. So basically, in the very extreme case, for a complete saturated CT, you don't measure any secondary current. Your relay input does not measure any current for a short amount of time. Fully saturate, all the current goes through that excitation range. Typically, when we calculate protection differential setting, we also estimate with not only symmetric currents after saturated CT, but it's a DC saturation is based on the X over R ratio. So the closer to the big chunk of inductors, such as in the proximity to a generator or to a big transformer, then you will have a large X over R ratio that will actually increase the likelihood of your CT situation. A CT can be modeled by a perfect current source in parallel with the exciting impedance range. So this is really not. It's basically a review of the CT characteristic. The exciting impedance is only very high, but during CT saturation, this impedance is basically reduced to zero. So all the currents to migrate instead of to your relay current. In saturation, exciting impedance drop at very low value, and CT appears to be short. And so, however, we have to understand that for a properly sized CT, according to your system characteristics, power system characteristics, your source impedance, everything, if you run a proper source studies and everything, your CT is not the CT will saturate under external fault, more or less, but it should not saturate right away. Any properly sized CT, you should allow a certain time in milliseconds that the CT can authentically reproduce the secondary current relay. Okay, that's very important. This kind of situation is very important in any low impedance bus protection. Modern bus protection actually only requires maybe down to 2 to 3 milliseconds of healthy replica of the primary current for the bus protection to operate properly, even in external heavy CT saturation conditions. In other words, the CT must not saturate before, let's say, 3 milliseconds, which is not really a demanding Uh, it's not too demanding because for any properly sized CP, you should allow at least that much room for proper CP operation. Okay, so issues affecting busbar protection selection. Bus arrangement, there's fixed switchboard. We went through that. Availability and characteristic of current transformer. We went through that. Performance requirements. Typically, for modern busbar protection, you need to be, when there's a busbar, you want to clear out the fault with high speed. You need to be dependability. You need to be obviously sensitive enough to operate for any type of bus fault. And also, the most important is you need to be secure. You need to be selective for external fault, even under severe city situation condition, you should not operate. The next couple of slides, we're going to introduce a different type of busbar protections. Okay. First, differential. There are multiple different ways to protect the busbar using a differential type of philosophy. First, differentially connect overcurrent, percentage restraint differential, high impedance differential, and partial differential. And then the second one is zone interlock scheme, and then the backup scheme. Okay. First, what does it mean by differential connected overcurrent relays? So if your fault level is not so high, okay, and you want to save some money, or you are pretty confident that the CT you selected for your system is the rating is high enough, and then you are very confident that you run thorough studies that you will not saturate, or you and then in that case you probably can apply a simple overcurrent element here to protect the bus. As you can see, if you differentially connected all the CT circuit before, basically you summarize them externally to the wires and through wiring, and then connect it back to the relay, you can effectively this is the differential relay. What's the difference between this and the modern, numerical busbar protection with differential feature? Is that this one does not account for first the CT measurement error. For example, remember for any CT, for C-class CT, you have to account for the worst case 10% per CT. So if you have a differential, the worst case measurement can be 20%. Okay, 20% of your measurement. So that's even under normal loading conditions, you can have up to 20% worst case scenario of your false differential current due to measurement error. Okay, and then this also does not typically a relay connected this way, applied this way, does not offer any solutions or any solution to counter CT saturation. So basically, you have to be very confident that the fault level on the bus will not cause the CT to saturate. Okay? Or once any CT saturates, how high the false differential current can be. So you have to set your pickup level higher than that. So in other words, the sensitivity, you will lose sensitivity with the scheme. The scheme cannot be set too sensitive. Okay? That's the downside. Okay, as you can see, for the external fault, you basically you have all the current coming out, and this is basically a differential circuit. As you notice that if this one, as soon as any one CT saturates, this current going through the excitation branch will become your differential current, effectively. So that's why when you are planning, when you're calculating your setting, you want to make sure your pickup is higher than this. This is for CT saturation, as I mentioned before. Even during normal operating conditions, normal loading, you have to take into account of the CT measurement error, which can be as high as 20% if you use C-class CT. Okay, so example, this is the summary. Application is okay if the symmetrical CD cyclic occurs less than 100 amp, which basically what it says is the fault current is not too high. Okay, so if it's not too high, the likelihood of the fault current saturating your CD probably is not that high either. So you can rest assured that I apply my overcurrent relay, with the setting higher than the expected measuring errors, and that should be sufficient. A burden less than rated basically means that okay, I would not cause unnecessary. My burden means for example, from the relay, from the CT to your relay, the cable run is not too high, the impedance is not too high, the resistance is not too high, then it's not exceed the rated burden, so the CT is not likely to saturate. And typical peak-out setting is high, as I mentioned before, because you need to account for those the CT mentioned errors. Okay, so now after those, what we covered before, the overcurrent relay, simple overcurrent relay connected in a differential circuit. So that's a very primitive, let's put it, primitive busbar protection. Now with the technology, with the progressions, and with the focus and security, operation security, vendors start to add restraint to the relay. What is the concept of restraint? What restraint does is, if you have restraint winding, basically, for the higher the current, the higher the current through the restraint winding, the higher the operating current that you need to operate the relay. So basically, effectively, the restraint concept is it make it harder to operate a relay when you have current going through the winding. As you can see here, this is a very this is the exemplary schematics that shows how restraint feature works. Let's say if you have for external fault, this is the external fault right here, and you see the current, the CD go through here, and when the restraint is calculated when you have when the current through and from the winding is different. So here you see you have 20 amp restraint, you have 40 amp. The total is 60 for external. For the internal fault here on the bus, right on the bus, you don't have any restraint. So if we look at for every single restraint enabled type of relay, you will have some type of curves like this. Of course, this type of relay is not modern numerical type of relay. But again, this just illustrates the concept of restraint winding. As you can see, if you have restraint winding here, you have a certain restraint currents going through the winding. Okay, and on the plot, you can see how much operating current you need. A higher amount of operating current to start or to generate the sufficient torque to operate the relay. Okay? We're talking about torque. Obviously, this means the whole electromechanical type of relay. Okay? But it's the same concept. So the higher the restraint current, you can see you need a higher amount of torque to really operate the relay. So that's why for external fault, actually, because of this restraint feature, you make it more secure. You need more operating torque to operate the relay. You can see here, as an example, if you have 55 amp of restraint, you need about 7 amp. 50 amp of restraint overcomes 7 amp of operating current with one restraint winding. If you have two restraint winding, you obviously need you need even more operating current to operate. That make it more secure. So the summary for multi-restraint percentage differential, good sensitivity, good security, allows other relay on the same CD core, different CD ratio between auxiliary CD, slow compared to high impedance, but scale is relatively fast. Number of feeders is limited by the restraint winding because this restraint winding conventionally electromechanical relay, how many CT you can, how many feeders you can protect in the busbar zone, or really with this multi-restraint type of relay is really limited, restricted by the number of restraint winding, obviously. And each CT is directly wired to the relay. And so, because of this number, the restraint on the size on the restraint winding is not easily extended. Next, it comes to the high impedance belt protection. Okay. So, for the high impedance belt protection, it's very similar. What you did is you put a high impedance, like over 1,000 ohms impedance, in series with your winding, with your relay operate winding. Basically, you have a high resistance here, right here. It doesn't show it here in this drawing, but this is your relay winding. You have a huge resistor here, and then to protect about over voltage, you have MOD typically to limit the over voltage. Okay? And how the relay operates, instead of you calculate the relay operating current, the relay really operate on the voltage. Okay? So this really a voltage operable relay. How it works is high voltage will develop an internal fault. Okay, so when you have an internal fault right on the bus, or the fault current going through, as usual, push in through the high resistor, obviously you will generate a super high voltage across the relay. Basically, this is the voltage. Imagine this is the voltage relay measuring across this branch, then you will have a high voltage value. And obviously, you will operate the relay. If your set point is on a certain voltage level and for internal fault you higher than that, you will operate. However, one thing to make sure is in that case, the relay you have to make sure sometimes some requirement is to actually short this resistance after the relay actually operates to actually reduce the amount of time that of the over voltage condition. That's very damaging, not only to the relay, but also you also stress all your insulation on these cables. So you want to make sure you limit that operation as short as possible. But typically, the operation time for the high impedance bus protection is not cycles. It is not a concern. The voltage units, because this, as I mentioned, this is a voltage protection, voltage units must be set higher than the maximum junction point voltage for any external fault. So you have to assume that for any CT that's fully saturated, the resulting voltage across this branch, and you add a certain ratio to it and make sure your set point is higher than that. That's how you set it. And at the meantime, with this set voltage, you also have to check that your sensitivity, that the currents that need to drive the relay with this voltage set point is also low enough, which means it is sensitive in your condition. Because when you run a short circuit study, you know at this fault at this point, at this geographic location, in this system location situation condition, is how many fault current will flow. Okay, how many fault current will go through here? You have to make sure that current is higher than your sensitivity. You need to check at that certain voltage step. So basically, you need to calculate your operating voltage. You need to also check your sensitivity. The two main things behind impedance bus protection. High impedance bus protection is typically very reliable, very fast, and very sensitive. Okay. Typically, it's sub-cycle. So these are some formulas to calculate how to calculate the voltage set point and how to check the sensitivity. So basically, you assume this branch, okay, is fully saturated CT. Like for example, let's assume that the CTB is fully saturated. So you short this one. So the voltage that apply the resulting voltage across this branch, okay, is basically your fault current going through this RL, which is your lead resistance, and your CT coil resistance. Okay, so your CT resistance and your lead resistance. This is for three-phase fault. the worst conditions actually are your single phase fault, because for single phase fault, you have a neutral return current. So you would have another resistance here because you go through the same lane back to your CT. So in that case, you have to count twice of this RL resistance value. But in general, the calculation is very straightforward. Your relay setting must be higher than this maximum voltage that can be imposed to the relay winding during external fault when the CT is saturated. And as I mentioned before, with this VR setting, you're going to calculate what is the current, okay? Not need to drive, not what's the juice, what's the current that the relay needs to drive the various components of this circuit. For example, that includes your excitation branch, that includes the current through the resistor and through the MOV. Typically, the current through the MOV can be ignored. It typically are very small. Okay. So you need to calculate this, the minimum currents, and check with your full study to make sure, oh, okay, my minimum current is small enough. I have plenty. My actual flow current is high enough. It's higher than this, so I need to make sure that the relay will operate. Expensive enough to operate. There are some criteria or reminders to note. One objective is to keep the voltage and IB low. Obviously, IB we want to keep it as low as possible, so your relay is as sensitive as possible. Okay. So as you can see, the I gain will be affected by the number of branches that you parallel together. In other words, the number of feeders, number of gates in the bus zone. In theory, for high impedance bus protection, you can actually include multiple unlimited amount of the base of the branches. However, it's limited by the it depends on how sensitive you want to protect. The other thing is you want to keep the PR, the voltage low, because you don't want to have a high voltage here, because for each cable on these leads back from between the CT and your relay, there's a certain rating on the cable insulation voltage, right? You don't want to constantly continue to stress that voltage. Okay? You want to keep that low as possible as well. Also, there's also safety consideration as well. So one way to do that, because as I mentioned, the VR depends on really the voltage drop across RL and RCT. RCT, you probably cannot do anything with it because it's the manufacturing design. But this RL, you can. Basically, if you limit the distance between the relay and the CT to as short as possible, you would lower this RL, and your voltage of VR can be reduced accordingly. How do you do that? So practically, the idea is you want to parallel. Okay, this is the parallel point. You want to parallel your CTs as closely in the yard, outside of your control building, out of the relay, as far from the relay as possible. Basically, as close to your CT as possible. In that way, effectively, you are reducing your RL, your lead. There's also a paper that published a couple of years ago in WPRC. There were tests. There's a reminder. There's a very good material there saying it indicated that if you set VR higher than that of the CT midpoint voltage, for example, if you have a C400 CT, if you set your VR higher than 400 and you use that value to calculate the sensitivity, then you will get error. You will introduce error in your final IMU calculation. What it does is basically the IMU you calculate from using the curve will not be accurate anymore. The reason is if you if you use the if you set the setting VR equal to 500 volt, for example, is way higher than the 400 rated value, that CT actually is saturated, has entered the saturating region in the curve, and you use that to interpret the currents that would introduce error. So try to set your VR as low as possible, and then definitely below the 400 amp your rated CT value. And the other limitations or rules for high impedance busbar protection is all CT should have the same ratio and make the tight interpret. Next, we gradually migrate into some of the modern low impedance type of relay design, and this really I'm not going to emphasize or stress focus too much on this, because this really is a ABB design of the very old, proven, reliable RADSS. Some of you may have known or used, applied this type of relay. It's very fast, sub-cycle, and it's the static type of relay. Okay? And of course, it's already phased out, but the concept, the algorithm, the protection algorithm has been, borrowed and used, updated throughout later generations of ABB busbar protection relays, such as RED 103, RED 521, and to the modern Reliant family 670 and 650. We are all using the same principle. Of course, we're not using a static type of design, using diodes, using transistor. We're not using that anymore. We don't need auxiliary CT anymore, but we're using sampling and numerical approach, but the idea is the same. Okay? However, and one thing to note that this type of low impedance design really was developed to lessen the restriction imposed by high impedance, such as it requires that you have the same CT ratio and magnetic characteristic of all the CT. Okay, and also you can actually seriously connect the CT. The CT does not have to be dedicated to the busbar. You can actually connect in series to other relays, for example, meters. I'm not going to go through too much detail on how this works. Basically, the idea is the same. You have the incoming current, you have the outgoing current, and the differential is the sum of it. You subtract the two. The difference between the two, you get the differential current. So that's still the same differential current. So for internal fault, as you can see, you have a high differential current. For external fault, you should have no differential current. But upon CT saturation, you could have the false differential current that you need to watch out for, and the relay need to be sensitive. Need to be selective and to be able to block for operation. Again, modern relays really. Again, I think I went through this. The advantage of this is lower CT requirement, allow much higher CT loop resistance, and fast operating time for internal fault. Now, as I mentioned, modern relays, especially ABB, we are using the same algorithm. But again, what's different is that we obviously take the numerical approach. So then we analog equal current instead of going through these auxiliary, mechanical transformers and diodes. We go through the digital signal processor to simple and quantize to numerical numbers. Basically that's this is the same technique applied to any modern relay, selective relays. Same algorithm is being used, and so really the same advantage as before also apply to modern relays. The difference is we use sample, all the analog input current are sampled, and then after they are sampled, they are fed to the digital signal monitor to, for example, the DFT algorithm to estimate the phasor value, and those phasor value are feed into various action functions, for example, differential function to calculate differential current, to calculate restraint current, everything numerically instead of through the static transistor. Again, the critical factor is the time available to make the measurements, the time to saturation. So in the modern relay, typically, if you can allow a 3 millisecond window for the CT not to saturate, properly reflect or produce a genuine secondary current, that's enough for the modern numerical busbar protected relay to properly restrain from external. So typically, modern protected differential relay will always use this type of slope type of operating characteristic. It's very similar to the one I introduced before on the mechanical type with string winding. It's very similar. On the x or horizontal axis, you have your restraint current. On your vertical axis, you have your operating current. So the higher your restraint current, obviously, it takes more effort to operate. And it takes more operating current to operate. So in a sense, basically, you increase your the stability and security within the high current region. This is the region where CD saturation is most likely to occur. And everything else, these are specific ABB design. For example, we fix the curve to 53 degree, 30%. So really, and these are the 45 degree points with the ID. These are standard ABB design. Different vendors have different design, but we have all used the same concept with the numerical type of phasor estimation technique, signal processing technique, and also with the curve, the slope type of characteristic. You can have two slopes, you can have one slope. But they are all the concept. Now, I believe the next are some animations to illustrate the different system phenomenon that can be imposed on the busbar protected relay. Okay. First is internal flow. As you can see, there's a load current in IN. The small I stands for a peak current, or just the raw current, raw measurement. The capital I stands for the RMS measurement. So it's the phase. It's the RMS measurement. Okay. So the RMS for a window, over a window, estimate over a window. So as you can see that, and the relay operate only on the RMS measurement. They don't operate on the raw or peak value. As you can see, during normal operating loading situation, you have a very stable low current value. But once you have internal flow, you can see both inputs. The inputs start to jump high, okay, and then output start to decrease. The reason is for internal flow, basically there's no output, there's no I out. All the currents are going into the flow. So that's why you have a high differential current. You have a high, relatively high IMS current, and then if you subtract that from the output current, capital I output current, because it is virtually zero, you have it's above your differential setting, and you should operate. Okay, this is a note here. When the differential ID is greater than the differential operating level, which is your set point, how about external flow? You can see the same before with normal loading. As soon as there's an external flow happens, you can see that the IN and IL actually try to match. Actually, the IL actually try to climb and match the IN for a short period of time. So this is why it's critical to have at least 3 milliseconds. Of non-saturating time. Okay, you can see IL try to match it, and based on this, the relay will know that I see my IN and IL rise simultaneously. At least for this short period of time, I can conclude that it's external flow. Okay, and then I will restrain. I will block the operation based on that. You can see the relay detects that in and out at the beginning of the external flow, and then because this short interval in and out and restrain properly during external flow. Although you can see after the CT starts to saturate, like hopefully beyond the 3 millisecond mark, they start to drift apart. Okay? Either on the IMS perspective, they start to drift apart, and you have to start to develop the false differential current. But because you have this portions that of healthy sections that the relay could deduce that it's an external flow condition, so the relay will restrain and block from operation. How about during the open CT situation? You have relatively, because of this different scale. Okay, we can see the scale is about 1.7 per unit, about 1.4 per unit. This is a healthy load condition. As you can see, you basically in and out are the same because it's a normal load. There's no differential currents. Okay, the relay is stable. But once one of the CTs start to one of the CT gets open accidentally or shorted accidentally, that relay input stops to receive measurements on that CT. You can see that the I in remains the same, but IL starts to drop. And as you can see here, the IMS, for the IMS perspective, they start to drift apart. Okay? And what you will see is, if it's over, if there's a multiple setting, you can alarm, you can trip. Depends on what you like to do. But just note that open CT is a very dangerous situation. It can cause high voltage, and it's a security safety concern to operating crew. So really, it's up to the utility whether to trip or to alarm this situation. They need to do something. So modern relay typically also have an algorithm to detect open CT. Obviously, you can, but because you can decide whether to trip or to block and alarm. Okay. In summary, other features in modern numerical bus IED. Okay. So each device is capable of connecting multiple bays. This is called numerical numerical relay. You can basically numerical relay. You can like for example in ABBs design. You can have a 3-phase CT, or you can have single-phase CT. Single-phase CT, obviously, you can connect all the way to, for example, 24 input, 24 bays. You can connect a bus with 24 bays, so you need 3 buses. For 3-phase CTs, you can 24 divided by 3, you can protect all the way up to 8 bays. So that depends on the size of your bus bar. You can design and specify the equipment. They typically have multiple different differential zones, dynamically based switching, zone interconnection, and checksum logic. So as I mentioned before, this is mandatory for those type of bus configurations, such as double bus single breaker, where the bus zones, the CTs are dynamically connected to the bus. So there's no fixed number of CTs connected to each zone. So you need to know, depending on the disconnect status, for example, to know exactly how many CT and which CT are connected to certain bus bars. External false CT saturation detection, as I illustrated before, and open CT detection. Line zone, end zone protection, backup protection. This I'm going to introduce. Okay, what is blind zone? We kind of introduced a little bit. I mentioned a little bit earlier. The blind zone are between right tank CT and breaker. So, for example, on the fault here, it is the blind zone. The reason is for the breaker that's normally closed, zone A will operate, like introduced before. Zone A will operate, which is good. However, zone A operates doesn't mean it still did not pick up the fault. It did not clear the fault. The fault is persisting. Because the zone B will restrain based on the polarity of connection of the CT. But then on the other hand, when the breaker is normally open, okay, zone A for the fault here, zone A will still operate. However, this time the overtripping is unnecessary. you're still not going to take out the flow, and while zone B is still reserved. So what is the solution? So at least in our ABB relay, you can connect your breaker status, okay, to your busbar protection function. Okay. So what it does is, when the breaker is open, we'll remove this 2 CT to each of the zones. So what happens is when you see the breaker is open, okay, let's use the breaker closed scenario. The breaker is closed, off hits, zone A operates, which is good. The zone B restricts. But when the breaker is open, it indicates to the bus zone that breaker is open. You will take out these 2 CTs, okay, internally, okay, through algorithm, through programmable logic. You take out the CT to the zone. So what happens is, for zone B, if you take out the CT to that zone, the zone B will operate, because this fault effectively becomes an internal fault to zone B. So really, so the time it takes to operate really is still pretty fast. Although it takes some delay, you need to wait for the breaker to open first. So I would say, with modern breaker, 2-3 cycle breaker, let's say you can open in 4 cycles. But however, if you wait for the breaker fail, backup protection to operate, you can wait up to 9, 10 cycle, 11 cycles. No problem. Still faster than doing that. Okay. Now, let's say when the breaker is normally operate open, you do not want zone A to overtrip, because it doesn't serve any purpose. You could have this part of your bus bar. You could have this part of bus bar in service as usual, not uninterrupted, undisturbed. So what you do is, again, when the relay sees this breaker is open, automatically you will take this CT out of zone B, out of zone A. So in other words, for the fault here, zone A is not going to operate because there's no CT here. But again, zone B, because the CT is gone, is removed, disconnected, you will operate for this fault and clear out the fault completely without disturbing anything in zone A. So this is a very smart feature. Typically, this type of configuration you see for the main type of bus configuration. Imagine you have a transformer here, you have a transformer here. Okay. Now let's look at this new configuration. Imagine this is the bus bar for a breaker and half stations. This is the main bus bar. This is one feeder, one feeder, one feeder, one feeder, and you should have another breaker here, another breaker here, another breaker, and it could be a line, transformer. But this is not a main substation. That's the point. Imagine this as the breaker and half. So now we see this red line and the blue line. What are they? The red line enclosed by the CTs. We call that the measuring zone, measuring boundary, measuring zone. For the breakers, the blue line enclosed by the breakers, we call that the protection or the tripping boundary, okay, the clearing boundaries, if you like. So as long as you don't have the matching protection and tripping boundary, you will have a blind zone or end zone scenario will appear as long as you have a non-overlapping protection and end zone like this. You don't have the overlapping, and you will have a blind zone in the middle. Okay? It's very similar to what we illustrated here. Okay? So this is for main timing. This is for the high voltage, for the extra high voltage breaker and half station. What I want to stress that is, there's no different. These two scenarios are very different. Let's look at number 3. Okay, point number 3. For the fault in this zone, okay. Again, regions not overlapped by both red and boundary are blind zones. CTs are used for both feeder and bus protection measures. So let's imagine this CT. Okay, because typically, as I mentioned, for a breaker and a half type of configuration, you will not typically have a overlapping CT. You will not have a CT here. This is the light tank. This is the light tank CT. So you will only have in
however, I have to admit that this is a little bit for the illustration purpose. Typically, when you design a station, you will actually standardize on which side of the breaker you will put your light pace on. You won't put one on this side, one on this side. It's a little bit exaggerating. Anyway, but it's just trying to illustrate the points here. So this is very common arrangement for breaker and half stations. On number 3, for the fault here, the measuring CTs here can be removed to avoid over-tripping conditions. Again, when the breaker is closed, fault hits, the busbar protection opens. However, the fault is not clear, right? Fault here, the fault can be fed from this side, from the line here. So something needs to be done. So again, when the breaker is open, the solution is to enable a fast overcurrent or any type of overcurrent sensing function here to detect that when the breaker is open, enable that sensing function, and once that function reads or measures any current, because when the breaker is open, it reads any current, you will send a transfer trip to the line, to a transformer, to the other side of the breaker. Probably clear, and it will be relatively high speed. And again, when the breaker is open, you don't want to over trip, so you take out the CT to prevent the busbar protection from tripping on this one. For 4, this is the under tripping scenario. For the fault hits here, okay? For the fault hits here, let's imagine there's a transformer here. Fault hits here, this transformer protection will open. You open this breaker. Okay, you open this breaker, but the fault still here, still fed by all the other feeders to the bus. So again, how are you going to force the bus to operate? Again, you need to, when the breaker is open, you want to remove the CT. When you remove this CT, this fault becomes internal. This busbar protection, this busbar differential circuit, and the busbar protection will operate to take off the fault in high speed. These are, in summary, these are some features that you can address the blind zone end zone issue. Other distribution medium voltage busbar protection methods, we have the partial differential. Basically, what it does is that, for example, if these are the load, these are the source. Typically, you see this a lot in main timing or medium voltage type of distribution or distribution level substation. You have all the sources. Typically, what you do is you sum all the sources together, and this overcurrent elements will have to coordinate with maybe this is the feeder. You have feeder protection. If you have a fuse here, you need to coordinate the overcurrent with the feeder. The advantage of doing this is you don't have to coordinate first, of course, then you kind of save yourself from having to install every source. You don't have to install one relay for every source. You save that much that amount of money, the resources. But the other thing is, by doing this, you also don't have to coordinate every incoming source feeders with the outgoing feeders. You don't only need to do one, right? You need to do one. That's the advantage of doing this. It's called partial differential. However, partial differential means coordination is still required. You need to coordinate the operation heuristic, the curve, with this relay to make sure the fault downstream on the feeder, on the load feeder, operate first. So you have to give this fuse the opportunity to clear out the fault. A blocking scheme. To protect this busbar is another method to do it. If you don't, if for example you have a dedicated arc flash protection, for example, the bottom arc flash protection can use fiber conductor to sense the light and operate in very short amount of time, a couple milliseconds. You don't really need a dedicated busbar protection here, but you still want to clear the fault on the bus relatively quicker, right? what you do is you rely on some sort of blocking scheme. So if you have fault on the feeders here, you like the feeder to pick up because the 50 elements, supposed to be 50, 51 elements. The pickup functions of this 50 elements, 51 elements will pick up, and conventionally you can wire that output that pick up the signal, drive the output. You wire the output back to this main incoming overcurrent relay to block. So in other words, for the fault on the feeders, this incoming overcurrent relay will restrain. Only when the fault is not on the feeder, right? For example, it's right on the bus, for example, assuming there's no reverse feed, there's no sources on the feeder side. For the fault on the bus, the relay, this main incoming relay will operate after a certain delay. However, that delay is critical because you need to estimate, you need to allow a certain time delay for the communication for the relay, for this relay to operate first, and allow for plus a margin, and allow for the communication delay as well between the two devices to communicate the block into common. Okay, so again, in a conventional way, through hardwire, you probably would you need a safety margin, you need the overcurrent protection start delay, output delays, about 40 milliseconds. I'm not sure it's probably a little bit long, but a start delay with receiving delay means it's the input. You connect back to the input of the main incomer. There's a delay because there's, for example, delay disturbance. The debouncing time from the input, for example, in the main incomer. You need to account for that. On the total, we add it up. You probably need to wait for about 100 to 120 milliseconds. However, in the modern communication scheme, modern relay also support the new substation engagement protocol, IEC 62050, and in particular, the GOOS, generic object-oriented substation defense type of application is relay-to-relay communication using substation through substation automation Ethernet network. With that, you can probably reduce the amount of time. The consideration is still the same. However, because it's not hardware, you don't go through the mechanical I/O module, the binary input module, binary output module. You don't need to wait for the debouncing time. You don't need to wait for the contact closing time. So relatively, you can reduce the time, the delay down to a certain time. Okay, and then the communication between for the Ethernet packet to transmit to flow through the network. To pass through, to go through the network, with the total of these relatively conservative estimation timing, you save about, let's say, 50 milliseconds. This is the same blocking scheme applying 61850. So I almost reached the end of my presentation. So this is a summary of the different busbar protection schemes that I have introduced throughout this webinar, as you can take a look. So basically, they are pros and cons to the different types of busbar protection schemes. But in general, really, as we can see nowadays, more and more the trend is of busbar protection. The migration, the progress is progressing towards the low impedance approach. Really, you don't really see a lot of high impedance relay anymore. At least in my area, at least most of the high impedance, old high impedance busbar protection has been really updated, retrofitted with low impedance, modern numerical low impedance busbar protection relay, because they can offer the same amount of sensitivity, security due to the internal algorithm for CD saturation to overcome CD saturation and even CD opening and closing. And also the size really is slimmer. You don't need extra impedance, and you don't need to worry about the high voltage that can be induced during the fault, during the external fault especially. So you don't need extra hardware, extra space to run those resistors, MOVs, for example. Also, it's more flexible. You can connect multiple relays together using the same CT, but in high impedance approach, you need to have your dedicated CT with matching characteristics. So the requirement is more stringent for high impedance. So that's why the trend we see now is more and more towards low impedance. And also modern numerical low impedance busbar protected relays are all equipped with modern substation innovation communications, such as the one I introduced, that you can actually customize for the blocking type of scheme, for reporting, for interlocking, for example, as you wish. So that's why the trend is toward low impedance. The recommended reading after this presentation is obviously the IEEE guide for protected relay application to our system, C37234. If you have any question, I welcome your question, and you should expect to receive a link to an archive of this presentation. I'm not sure if you will be emailed to a link, but at least in the same website where you register for this webinar, you should see after a certain time, you should see a recording of this presentation. If you, by any chance, you would like to refresh or revisit some of the concepts I introduced in this presentation, feel free to do that. For more information on UV protection and control solutions, please visit abb.com. That's the end of my presentation. Thank you.
Jack, can you see the question?
Yes. Okay.
Do you want me just to read them? There's only two right now.
Our current and voltage sensors are using NC switchgear for utility customers. I probably missed something. Our current voltage sensors are used in the NC switchgear for utility customers, which typically do not have saturation issues. I believe you're talking about the sensors, which they're using the Faraday law, the optic sensor, I guess, Faraday law. I think that's what you're talking about. Yes, actually, in fact, that's our latest technology. We call it process bus. Actually, it's part of the 61859-2 standard. It's called process bus. And yes, ABB GIS gears actually does incorporate with the voltage and current sensor on there. And then you feed the output of those sensors to a box we call the merging unit. Out of the merging units, the data stream is the standard 61859-2, and that can be subscribed by 9-2, 61859-2 support data. It doesn't have to be ABB related. Any vendors related, Siemens, Schweizer, GE, as long as they claim that as long as they are proven that they prove that they support 61859-2 data stream, they can subscribe to that CPAP measurement and operate upon that. What is the most common way to avoid CT saturation? How can you choose the CT ratio to avoid saturation? Well, I mean, this question is really related with is really regarding to system planning, protection system design. So really, you have to look at first of all your CT. The CT ratio cannot be too low, right? But you don't want to be too high, because the reason is if you overspec your CTs, then the accuracy for your typical low current, if you have the 2000 amp low current on the bus, maximum low current on the bus, you don't want to spec a 5000 amp CT, right? You have to kind of relatively,
in proportion, you have to consider your typical low current flow. And then typically CT has a factor, overloading factor. Usually I think it's 1.2 or something. So you can also adjust that, play with it to make sure it's sensitive, accurate enough to detect the normal operating low currents, but it also is high enough to overcome CT saturation. So as I say, CT saturation, really the relay does most of that. You just need to give the relay enough time. 3 milliseconds really is not a lot to ask for. So as long as you size your CT ratio properly, you know, it should be okay typically in modern relays. Yeah, and also, you know, you need to take into account your system X/R ratio, which typically is the DC offset that saturates the CT. It's not a symmetrical current just by magnitude. Okay, 20 times is not simply that. It's actually in combination with your the DC offset, which is typically caused by your X/R ratio. So the more inductive your system is, really in proximity, for example, to a generator, the CT is prone to saturate more easily. So you need to calculate that, and you need to calculate your current to saturation. There's an IEEE formula. Actually, I believe you can download that from the PSRC, IEEE PSRC website. There's a formula you can use. You enter your system parameter, the X/R ratio, your flow currents. What it generates is it tells you approximately how long the CT can saturate. And you can use that to, you can base on that to derive your delay protection operating parameter, like differential pickup. I hope this helps. Is there any questions? No.
All right, thank you, Jack. I don't see any more questions. If anyone does think of anything, they can always email myself or Jack, and we will definitely get back to you. We certainly appreciate you joining our webinar today. The next webinar in the series is line differential protection, and that will be on July 20th.